interest in promoting undergraduate research, and many of his students are in top positions in academia and industry. His areas of interest include technology-enhanced learning, algorithms, cryptology, discrete mathematics, puzzle-based learning, and algorithmic thinking. Professor Pandu Rangan is no stranger to IIT Mandi. He has come here multiple times, and during the early days of IIT Mandi, he has offered courses also here. And he is also known to be an excellent speaker, and so we look forward to this colloquium. Thank you.
Thank you very much. Thank you. It's wonderful to be back here, and then it's a great opportunity to address all of you and share my excitement that I enjoyed in the academic journey so far. Okay. The word man, manushya, and in Tamil, mannudal, means think. We distinguish ourselves from other species, at least that's what we think, by a special attribute called thinking. Of course, other animals do think. Right? Tigers do strategize. They coordinate and then attack. So there is a thinking, communication, everything is happening, but the thinking that is happening in the human minds is of a completely different level. That is why our race itself has been named after a very special attribute that we have called thinking. We use thinking for various things. We have emotions and we have imagination and we have various things, but one of the critical use of our thinking is problem solving. Problem solving, we do encounter problems and then we want to solve problems. A problem is any difficulty you encounter is a problem. I have a problem in my joint. I have a problem in my car. Any inconvenience is a problem and we want to solve the problems, right? Thinking begins. Initially, we think in some ad hoc manner to solve the problem. Later on, we would like to think deeply, we would like to formalize, we would like to understand various issues related to the problem, and then we have a much better solution evolving over a period of time. That's the way any solution has emerged. Anything that you see around, the light that you see, the mobile phone that you have, the first mobile phone is a very awkward, big stuff. Now, over a period of time, they have been enhanced. Now, you don't know whether you are carrying a camera with which you speak or with the gadget that you speak, you take pictures. It has come to that level of advancement. Everything happens that way. We solve certain thing in some ad hoc manner, and then over a period of time, we refine it. And what is happening in that process is the process of refinement or digging deeper is something that is very unique. It is called abstraction. We started doing a mental map. It's going to be in our mind. That's the reason why people say everything is created twice. Once in your mind and then the physical realization. The Egyptian pyramid, the Tanjore, Brihadishvara temple, everything, the architectural marvel to greatest of things that are created. First it is there in the mind in some form. And then it gets the physical realization. And the things that are in your mind, and then you put everything, a mental operation that you do initially is called the act of abstraction. What you do is you ignore irrelevant details and focus relevant details on a problem, and then an abstraction happens. Once you have that abstraction done and a simplified model or whatever that happens in your mind, the next thing that is happening in your mind is formalizing. Formal form, physical form. You need to represent. You need to communicate. You need to understand that through better means. Everything can't be some internal logical reasoning or mental manipulation, because human mind has a lot of limitations. That is the reason why you need to formalize it, give form. Physically, you have to give a form. And that is where human beings also have, over a period of time, evolved into great things. Right? So imagine, 5,000 years back, you are living in the cave, no Hindi, no Tamil, nothing. You just found 3 lines outside. You are coming back into the cave. Your friend is going out. You would like to tell him that there are 3 lines there, don't go. Today you can use Hindi, English, Tamil, whatever, and you can say that. How would have they said that? So there is something in your mind, and that has to be communicated, represented. So you have to give physical form to that. Only when you give that physical form, you can communicate to that other person. Right? Therefore, you do gestures. Now, over a period of time, you created symbols and so on. And that is where what is known as the formal thinking, or thinking through symbol or symbolic representation, the abstraction in our mind takes a form. And in order to make the reasoning and other things more formal, we began with mathematical thinking. Mathematics is something that is there already. That's why they said God created numbers, everything else followed. It's there in nature. You see one stone, you see 2 birds, you see a lot of ants, you see a lot of stars, you see a lot of trees, lot of leaves. One, many. You have discrete quantities, you have continuous quantities, water flowing, right? The time continuously varies, discrete and analog. You have. You also have what is known as a dichotomy in nature. It is and it is not. It is green. This is not green. This is true. This is not true. Right? So what you see is a dichotomy, multiplicity. All of them are there in nature. In fact, nature has got mathematics completely embedded in it. That is the reason why your reasoning process also, the symbolic process also, gets that mathematics naturally factored into it. Right? In our thinking, we quickly realize that 2 plus 3 is 5 is an independent fact. Whether you put 2 tables and 3 tables together, it is 5 tables. Whether there are 2 parrots and 3 parrots, it will be 5 parrots. It is not depending on the parrot or a table. 2 plus 3 is a 5 is something on quantities independent of the object. So what you see is object and the multiplicity or the associated math, distinguishing, everything comes into picture immediately. Therefore, what happened in our thinking and problem solving is, over a period of time, mathematical thinking becomes a natural way to abstract, formalize, and then reason out. So in the process of going from naive solution to sophisticated solution, earlier our bed was, we were all sleeping on the trees, right, on the trunk. The trunk will have awkward angle. Somehow we will try to adjust our body, and then that's inconvenient notion of a bed, and that is to be refined. The tree must be polished, and then you take a stone and rub it, make it smooth. So on. From there, now king size bed, queen size bed, and then with lot of cotton and various materials, memory foam, you can see that the bed has become way sophisticated. Everything has happened due to the formalizing, problem solving, mathematical thinking integrated into it. The moment you bring mathematical thinking, everything will become way sophisticated. Afterwards, the problem solving itself becomes a complete mathematical act. And that is the beauty of it. Now, without even the context, without even any physical entity, I have set of symbols and set of things that I work with, and then I can relate to the reality. Okay? Imagine, without mathematics, without formalism, just think for a moment. Again, go back to the Stone Age, right? Nothing. You want to convey that 15 days back I saw this fellow killing the other guy. How would you say that? 15 days back, you have seen, you know, in the distant past, he has done a Crime, he has killed, you have seen that, you know that. You want to communicate. Where is the representation of time? How will you say anything about time? You exist, you know, your mind knows. It's there in your mind. So you can see that calendar is nothing but a mathematical model. Calendar is a mathematical model of time. It introduces symbols like January, February, March, and in Tamil, Ani, Adi, Avani, whatever it is. In Hindi, you may have your own names for it. Doesn't matter. Basically, you introduce a set of symbols and meanings are assigned to the symbols and operations are introduced on them and you perform the operation. Now you have a week and month and other things, leap year, this, that, and now you ask various questions. You are able to solve the problem. You can represent the moment that mathematical representation comes. What day is 113,000? Is it Monday or Tuesday or Wednesday? You can now have a computation and then you can tell that. You are not there yet. You are not going to be there at all in 113,000. Still you can talk about it. That's the power of mathematics. A set of symbols, a set of operations, and once you derive that, an algebraic system is put in place. Once an algebraic system is in place, problem solving is done through this modeling. That is the reason why problem solvers always use mathematics as the principal tool. It can tell everything about the context of the problem. That's the beauty of it. Mathematics is not just the queen of science. It is the queen, king, princess, prince, everything about the science. Slave, master, all about anything that you are reasoning is coming through that mathematical thinking. It's an amazing experience. Thinking everything first in terms of math. The problem solvers and human beings, what is the second great attribute of human beings and the advancement of human race? Our ability to create and use tools, right? When we invented wheel, we invented printing press, and then various tools we have invented, and because of that, the progress was there. And now, human beings being a tool using species, the problem-solving tool computers have triggered a tremendous amount of deep rethinking into our problem solving. Earlier, problem solving means a mathematical thinking, a mathematical formulation, and so on. Not long ago, 75 years back, go back and then see the archives of the old papers. What do you mean by a computer? Anyone has an idea? What is the computer 75 or 100 years back? The term computer was still there. Anyone has an idea what a computer is? No calculator. A person. A room full of computer means a room full of people who are doing hand calculation, statistical tables, right? Solving differential equation, partial differential equations, mathematical calculations of the room full of guys. The RAND Corporation, the defense R&D of US, they will have people to solve optimization problem and various problems faced in the World War and other things. How was it done? No computers in 1920s. Humans. In those days, by computer you mean a human who is doing numerical calculations, right? So, when the tools were done, the way in which we are trying to solve the problem itself has completely changed, right? Because you want to use the tool effectively. What is that which has brought in a major cultural change? It is not just the speed of the machine that you have. It's not just the technology that you have. How do I enable this machine to solve the problem? How do I use it to solve the problem? Is a question that started coming up. So in mathematical thinking, you have various issues you will address. Does it exist? Is the solution possible? Okay. So you have upper bounds, lower bounds, non-existent result. Square root of 2 is irrational. It cannot be represented as a ratio of two integers, PQ, right? Non-existent results, impossibility results, possibility results, existence, Rolle's theorem, mean value theorem. There exists a theta. F dash of theta is f of b minus f of a by b minus a, theta in that interval. You have that result, okay. I want to find that theta because it shows the direction and so on. The derivative is the slope. is defining the slope. So if I give you a function x cube plus 7x plus 9 and the interval 43, 71, can you find the theta? You have read the proof. It exists. You are convinced. You are logically convinced on that. But could you find that after reading the proof of the theorem? It uses some Taylor's theorem and some existential truncation and bounds and other things. And finally, you are convinced that it is there. But I want that value. I want that physically value. There is a depth at which if you dig and lay the foundation, you can build the 50-story building. Are you happy with that statement? There exists some depth, some D. There is a path from here to airport. There exists. Are you happy with it? Good to know there is a path from here to airport. But the point is, what we want is physically the path. I want actually the number at which I have to go deep and then build my foundation. That is computational thinking. From mathematical thinking, for solving the real world problem, we have to mature to computational thinking. In computational thinking, we explicitly work on values. We explicitly obtain the values. We explicitly construct an object, and we explicitly produce something that is usable in the real world. I want the path. You use the Google map. What does it do? It has to show actually the path. Which road you have to go, where you have to turn, how long you have to go, how much time it takes. Gives you a lot of information. Right? The physical path is there on the road. But then in your mobile also there is a representation of it. Abstract mathematical representation of it. In that, it physically computes and gives you the physical path, representation of the physical path. That is what is needed. In other words, you start with mathematical thinking, but then you must immediately progress towards computational thinking. If you go to the library and see the host of mathematics books, right? Quite a few of advanced mathematics, abstract ideas, and all of them are there. But what is useful for engineers and for computer scientists and other things are computational thinking based mathematics. What we want is that a good mathematical foundation, proper representation, abstract data type. In fact, computer science starts with abstract data type. What is abstract data type? It's a mathematical model together with set of operation. In other words, it is a self-contained algebraic system. Computer science is mathematics. There is no doubt about it. But the kind of math that we want is computational thinking. Right? Which is a very distinguished style of thinking. Mathematical thinking has got various things, emphasis on the logic, emphasis on the correctness, emphasis on the validity of the result, and sometimes the quality of the result. For example, upper bounds and lower bounds. The upper bound should be tight, the lower bound should be as tight as possible. Variety of math results you have. They are all good, they are all properties, but what we need to do is use properties to build computational process. Characterizations must be converted into computations, right? And properties must be converted into process. That is computational thinking. And once we have a good computational thinking in place, then we can think of the next stage of using the tool, namely the computers, to solve the problem. Right? So now we have a computers and we have a process, and we can now implement that process on the machine because I have an explicit computational steps. Do this, this, this and this. You will get a value or an object or produce something, and you can do that, get it done by computers. What happened was, the moment computers were put into use, they realized that there is something else need to be done. What else need to be done? It is not just the computational thinking alone that is important for our use of computers, right? Right now we are focusing on problem solving using computers, right? So for problem solving using computers, mathematical thinking is a starting point, computational thinking is a way to go, but something more need to be done. That is because The computational process is going to consume physical resources. It can use bandwidth, it can use number of processors, it can use memory, it can use physical clock time, seconds, minutes, and so on. It is going to use physical resources. What if your computational process is so complex that it takes enormous amount of time? Right? So, very well known things. You know that many of you, right? You have found out the determinants. Very simple calculation of a given matrix, finding the determinants. Finding the determinant takes factorial n steps, and a back of the calculation will tell you that factorial 20, even if you have a supercomputer that is doing 10 power 7 multiplications per second, to do 20 factorial multiplication, any guesses how long it is going to take? 20 factorial, 20 followed by an exclamation mark. That many multiplications you have to do to evaluate a 20 by 20 matrix and its determinant. Any guess how much time it is going to take? Try some wild guesses. What is that? More than the age of the universe. No. 20 factorial is fortunately not that much. It is going to take about 1,500 to 2,000 years continuously. You switch on the machine, the cursor will blink for 2,000 years, and then you get that number, one number, determinant. Absolute, it's a computational process, but then it is an unacceptably inefficient computational process. In other words, what we want now is algorithmic thinking. So what is algorithmic thinking? It is a mathematical thinking, it is a computational thinking, but additional engineering twist is given to it. Make sure that the computational process is efficient. So what do you mean by efficient? It must consume less resources when physically implemented on a computer. What are all the resources? You can think of anything that is important for you as a resource. Assuming that time is one of the critical factors, which is very true, right? You don't want your computer to take too much time to solve the problem. You write a C program, you have given a compile command, CC command you have given, and nothing comes on the screen. What do? You slap the screen, hit the keyboard. You don't get that A dot out immediately, right? So you are restless. Even for 1-2 seconds you are not able to wait. We want everything fast. Time is a critical component which we are focusing on. In other words, resource must be as least used as possible in the computational process. Therefore, I just not only want a solution, I want a computation solution. Also, I want that computational solution to be as efficient as possible. That is algorithmic thinking. Algorithmic thinking distinguishes, it's a unique way of thinking for computer science. This kind of a thinking is not there in other branches. It is not there for other problem-solving enterprises. When problem-solving using computers are to be used, a unique way of thinking is to be developed by everybody in computer science or anybody who is using computers to solve the problem. It's a fundamental skill, competence, knowledge that one must have, core competence, right? So what we have to do is that algorithmic thinking must be developed. Why it is crucial? The very existence of computers that you see today is an outcome of algorithmic thinking. How? Let us look back one interesting stage in the history. The computers, right? The earlier computers, when they were designed, they were using vacuum tubes and other things. But then there is one pioneering idea that emerged. Von Neumann. He has introduced the von Neumann concept, or the memory, concept of a memory, where he could load the instruction and the data and the system will automatically work. If it is a calculator, every time you have to hit, you have to press the key, you have to move the data, you have to give that, you have to give the command. It's a human operation. It takes lot time to move your arm and then press the key and so on. Whereas an electronic data transfer is 40,000 times to 50,000 times faster than your movement. Can a system automatically take the data and the instruction, and can it automatically execute on its own? The von Neumann architecture was proposed. People didn't believe it. What is this crap? He's doing that computers can be made fast, it can solve all problems very efficiently. Lot of claims are made, but then where is the proof? Why should we fund this project? The question was very critical. So von Neumann has to prove now that computers are really efficient, it can solve problems. And computers can solve any reasoning based computation. It need not be numerical. It is not just for number crunching. It can do non-numerical work as well. So non-numerical, problem solving, general purpose, we can do effectively. This he has to prove to the world. The entire world is challenging that whether this idea is good, should we fund it, and can we have the computer design and other thing be encouraged by funding this project. So von Neumann has to demonstrate now. Okay? So at the time, the major competitors were Hollerith's machine, which is used for census. IBM's forefather, right? The Hollerith machine was doing lot of sorting of the data, census data. There is a special purpose machine designed for that. And then in the mid-30s, there is a collator. That collator is going to use two sorted files into a single sorted file, right? And these two things were all there as a physical machines, and they were all doing enormous amount of processing at a breakneck velocity. Now, what von Neumann did was, he wrote a program based on an algorithmic thinking. He took the sorting problem, he has come up with a new efficient sorting algorithm. The normal sorting algorithm may take enormous number of steps. To sort 1,000 numbers, it may take millions of steps. He has come up with a method that is called the merge sort. That is what is probably taught in data structure course and basic courses. Merge sort he introduced in 1945, and he deliberately worked on algorithmic thinking because he wants to show the machine, the architecture that he is proposing is capable of outperforming any machine, even a special purpose machine. It is not designed for sorting. It is designed for problem solving. And this general purpose machine can outsmart a special purpose machine, is what he has shown by using a beautiful algorithmic thinking based solution newly designed for sorting, and merge sort is born. He implemented it, and then when he ran it on the computer of those days, it simply outsmarted that, and the whole world got excited about problem solving using computers. Oh, here is something that is a new monster who can do very many things much more efficiently. The very algorithmic thinking is what made the world turn its attention to computers, design of computers, implementation of solutions on computers, all of them. That enthusiasm started with one critical thinking, algorithmic thinking. Had he chosen an inefficient solution and had he shown the failure of that, people would have think that special purpose machine is good. For every problem, let us design a special purpose machine. That's how people would tend to think. The whole thinking, the entire science took a U-turn with the single progress of one algorithmic thinking that has completely changed the scenario. And now you see the benefit of that. The entire human race, benefit of computers and problem solving using computers, computers penetrating all walks of lives of all kinds of application. Everything started with that algorithmic thinking. That is when they started realizing that problem solving using computer requires not only mathematical and computational thinking and algorithmic thinking. And the algorithmic thinking started, growing up. And then there are several challenging problems for which they now want computationally smarter solution. Okay, very simple problem. You want to multiply two numbers, right? Let's say you imagine there is a 10-digit integer, below you have another 17-digit integer. Imagine two numbers. You want to multiply these two. How would you do? What is the high school method? Digit by digit, right? Use the least significant digit, multiply it and write it down, shift by 1. Therefore, if you have two n-digit numbers, typically you would require n square multiplications, n square digit operations, right? Each digit multiplying everything n square. What else you can do with this? You can't cut down anything. There is nothing to be smart about it because there is no shortcut possible. Every digit is different. You have a1 to an, you have b1 to bn. You have to multiply that with this. All numbers could be different and no formula, no shortcut, nothing is possible. Therefore, you must use n square. Multiplication was the major thinking, computational thinking, right? If you want to be smart, there is no way. In fact, perhaps you might have all known Kolmogorov, right? Have you heard about Kolmogorov? What is he known for? Anyone? Kolmogorov complexity, and then, but what is his fundamental contribution on? Probability theory, right? And he is one of the top Russian brains, and whenever he will go to various conferences, he will give mathematical challenges in cybernetics, mathematical problems in computer science. He will give some, and then he will throw a lot of challenges, algorithmic challenges, right? And around that time, that is the mid-30s and late 40s, you know, Turing has come up with a phenomenal way of looking at computation, and then what can be computed, what cannot be computed was resolved. Turing's thesis has done such a phenomenal work. The next thing is, okay, you can compute this. There are certain things you cannot compute, right? Computer science students might know about it. Let's not worry about it. Unsolvable problem. But there is a problem that you can solve. How well it can be solved? For this question, the simple multiplication which is needed for every number crunching, people were worrying about. And at the time, in the audience, there was a 23-year-old youngster who felt that, no, there should be some other way to do that. Let's think in a completely different way and then see whether we could do it. That is Karastuba. Karastuba was 23-year-old. Within 1 week, he heard in that Kolmogorov's one, he went back and then he came up with a brilliant method that is taught in every computer science course. Divide and conquer. An amazing algorithmic thinking paradigm. Paradigm means paradigma. Para means external. Daima means example. Externally displayed example. When you go to cloth shop and other things outside, or when you enter, there is a glass case in which dolls are adorned with the latest arrival of salwar kameez or pant shirt, whatever it is, right? It is a example of the pattern inside. So it is a representative pattern. The pattern of computation, that is called the paradigm. In computer science, paradigm represents a pattern of computation. Split the input into two parts. Solve independently on the subparts. Merge the solutions. Beautiful strategy. This is called the divide and conquer paradigm. And the divide and conquer paradigm was revolutionizing the algorithmic thinking. The way in which one can split, and the first one was a divide and conquer method. Karastuba's method was a divide and conquer method. And then there was a discussion on the seismic data analysis of studying the data after the nuclear explosion, right? And then there are the US research team which were working on the President's Scientific Advisors Council when they were meeting to discuss, and when they called the experts from IBM and other things, there was a big intellectual discussion on this, and the bottleneck was the convolution computation. And the convolution computation was again in a phenomenal manner using discrete Fourier transform. They could solve it in n log n time from n square, and that's n square is, even for 1000, n into n is 1 million. N log n is 1000 times 10, only 10,000. You can compare n square with n log n by comparing million with 10,000. That's the kind of a speed up, computational gain, efficiency. Algorithmic thinking can bring in marvelous, enormous amount of great computational advantage, speed up, resource consumption reduction, everything it can do. And that is the reason why the discrete Fourier transform has become one of the most used applications on earth as of now. Among the computational engineering top 5 applications in the world, DFT figures mainly because of the way in which it efficiently solves some of the critical numerical computational problems. So history is abundant with algorithmic thinking and the way in which we have to now go about thinking on solving problems. So computer scientists started specializing on this. That's what they would do. So what is that computer scientists are doing? They are solving mathematical problems, right? Whatever is the problem, first they get a mathematical model, mathematical representation, everything is math. And they solve only math problems. It doesn't matter whether you are solving a problem in ML or AI or databases or computer graphics or image processing or anything. It really doesn't matter. Whatever is the application that you are doing, you are all solving only the math problems. What difference that we do is, besides the domain level expertise, is how can I get the job done as effectively as possible? What are all the clever methods available for me to solve? How do I bring in efficiency and get the best mileage out of my solution? If the current solution is not satisfactory, how do I create a new solution which is better than what I have in my hand? These kind of thinking is what is characterizing the whole computer science community is abuzz, independent of the subtopic and sub-areas on effective problem solving. That is the reason why this is one of the core competence in computer science. Right? In fact, if you look into the job market and job opportunity, and if you look into the high profile people, they are not going to ask questions on programming languages and then the syntax of should a semicolon be put here, or in Python, what will you do, in C++, what would you do, Java. They won't care about those questions. They are skills. The competence comes in your algorithmic thinking ability. When a problem is given, are you able to see the way in which it has to be attacked? Can you judge the quality of the solution produced? If the quality of the solution produced is not good, will you be able to come up with a better solution? Do you have that creative ability? All these things are checked. That is the reason why algorithmic thinking is among the fundamental core competences. So, from the beginning of the human race to the progress of the human race, mathematical and computational thinking has helped. Ever since computers have come as a revolution, disruptive technology, and then when the human race started making enormous progress due to this one single tool, a completely new way of thinking it called for, and that is algorithmic thinking. Okay? So, what I am going to demonstrate in another 20 minutes or something like that, or by the way, how much time I have? I can fine tune accordingly. 15 minutes, okay. In 15 minutes, we have to optimize on time, obviously. I can't be talking on algorithmic thinking and keep taking enormous amount of time, right? So naturally we have to condense it, and then we will do that. Okay? So there are 2 case studies popped up in my mind for the discussion, but I would now illustrate what is computational thinking and algorithmic thinking and other thing using a different case study, because we have only 15 minutes and I want to make it a little more interactive and lively. Okay, so let's do this. Let us assume that we have we have 3 jars of water. Okay, you are able to see there are 3 jars that can hold water, and what you can do is you can pour the water from a jar that is containing more water to the jar that is containing less water, right? How much you can pour? You can double. That is the only thing you are allowed to do. For example, if this is 7, if this is 11, if this is let us say 13. Okay? What can you do now? You can pour from 11 to 7. This is possible. You can pour from 13 to 7. That is also possible. From a jar containing more water, you can transfer the water to the jar containing less water. How much you can transfer? You can double the content. So you can pour, therefore this can be made 14. If you have poured from this, that would have made this into 4. Now you have option. From 13 you can pour here. That means from this will become 9 and this will become 8 and so on. So what is an operation? Pouring of water from a jug containing more water to a jug containing less water by doubling process. Right? This is the computation. This is the operation. The mathematical model is 3 numbers, and you can transform one number to a smaller number by transferring the value equal to the smaller number. Okay? Now, with this operation, you have to empty one of the jugs. You have to empty one of the jugs. How will you do? Now tell me some suggestion. Just you do some mental work. Let us use the same thing. I will use a different page. Okay. So here I will have, let us say 7, 11 and 13. What's your recommendation? Take a minute. It doesn't matter. What is that? No, this has nothing to do with actually GCD, but even if you tie GCD, this GCD is 1 in all these numbers. Huh? No, well, now what I am asking is a concrete method, right? So the question is it possible at all? By transferring this way, will you be able to empty one of the jugs? The answer is yes, but how will you do that? But first of all, we do not know even whether the answer is yes or not. Okay? Now, if you want to do this, what are the recommendations? From where to where I would transfer? Think for a minute and then tell me. This is computational thinking. Because I have to do a series of operations to obtain a goal. What is the goal you want? For example, if A, B, C are the content, little later, one of them should be empty. Let's say at the time others may have A dash, B dash, maybe this has become 0, right? Or it could become 0, B dash, C dash, or A dash, 0, B dash. One of them is made empty. At the time others may have some amount of water. So this is your initial configuration, or what is known as input. Then there is a process, and process is the operation, and with this operation you have to solve the problem. Constructive method, right? So if you want to have the constructive method, what are the things that you would do? Suggest some, I'll finish in 15 minutes, definitely, but just to make it interactive, and audience should feel how when a particular, this is a problem that is stripped off from all applications, context and other things, given as a pure math problem. So a question, but I don't know what A dash B dash is. No, that's what. So what is the starting point? We need a concrete way of performing the operation, and we have to start and then carry it out, right? No, it is possible to empty one of them, always. Whatever is A, B and C. We have results for that, but let us attempt a constructive way of getting it done. Like Rolle's theorem, there is a proof that there exists a theta. There exists a way to empty it. How will you go about doing it? Because we need to have a computational thinking. Where will you start? How will you proceed? What are the... Let us consider just these numbers and then see whether you are able to think a computational process. Yes, level when they are equal, that is the only way it will become 0, right? At some point it should become equal, and then one you would pour on the other and that would become empty. Right now we assume that all numbers are different, like 7, 11 and 13. 13 into 11, that is good. So this will become 22 and this will become 2. Then 22 into 7, therefore this will become 14 and this will become 15. Yes, that is also correct. This is 28 and this has become 1. 28 into 1. Yeah, that means it will become 27 and this will become 2. 2 into 2, 0. Excellent. So here he has found out a method. Right? Beautifully done. Now, tell me how you are going to do if my first one has got 2,709.84 and 17896 and 1177948 liters of water. How will you do it now? Which one will you transfer and then how do you? Right? You can see that ad hoc thinking. This is how we start. We will start in an ad hoc manner, but then you have to make it more scientific, right? And then you have to make it algorithmic. You have to make it into a systematic way in which I can handle any ABC. Because it is true for any ABC, and if the numbers are given like this, how will you ever? Now you see that our ad hocism doesn't work here anymore, right? It doesn't generalize. There is no common pattern that you see. Paradigm, computational pattern, you are not able to see. So when you are able to see all of them, you become more sophisticated in arriving at a computational process that's going to deal with input, process and output. Okay? That is what. So what we can do is, I will give another example in which that process is very easily illustrated for on-board discussion. Let us say I have 10, 186 and 213 liters in 3 places. One of the beautiful pattern of algorithm design is in mathematics. Mathematicians know about it. They have all done it. It is called method of iterated improvement or method of successive approximation. You take some solution, make it better, and then make it further better, and keep doing it until you hit the answer. Progress towards the answer. If you visualize computation as a state, there is an initial state, there is a final state, and you have to progress through states towards your final state. Okay? So it is like navigation. Therefore, you monitor, have you progressed? Yes, question? Yes, we are going to see that. We will also see that in 2 minutes, right? So, one way we can make things progress is, you target the smallest one. Here it has 10 liters. Do something and make sure that I have a jar that has got smaller amount of water. That if you visualize as one stage, I can repeat that, and then therefore the content of the smallest jar is becoming smaller and smaller, and hope it will become 0. If there is no cycling, there is no infinite loop and so on, right? So how do I make things smaller? By transferring. By transferring means I have to remove the multiples of this one, because doubling means you reduce here and you increase in that. So by the doubling process, if I have to do, I can target like this. Let me remove as many as possible from the second one in multiples of 10. And when will I get 6 or the remainder? as many as the multiple of it. In other words, if I could somehow move 180 out of it, I will have 6. 180 is 18 times 10. 18 times 10, I should move from here to the first one. If I could do it, then I will have 6 left over in that. But how do I move 18? I can only double the content. 10 can become 20, 20 can become 40. That's all I can do. But I have to remove 180. So, because it is a doubling, consider the binary representation. You don't have to even consider binary representation. Consider 180 as 160 plus 20. So, I must plan it as moving 20 and moving 160. But how do I have only 10. So what I do is, I move from here 10 and I make it 20, and this will make 203. And now 20 is available, I move 20 and make it 40, this will become 166. Now I have 40, I double it until it become 160. So this will become 80 and this become 163, and again it will become 160, and then this will become, I have moved another 83. And now 160 is available. Now you move 160, this becomes 320 and this becomes 6. So I have moved 120. In other words, all I can do in general is the following. If I have A, if I have B, and if I have C, assuming A less than B less than C, if B equal to Q times A plus R, right, this is A, this is dividing B by A, the remainder is smaller than A. Therefore, I have to move Q times A from this, minus Q times A. How do I move Q times A? I have only A, but I have to move Q times A in a doubling process. So I can take the binary representation of Q, and wherever there is 1, that much I can move. Wherever there is a 0, there is a third one. From there I will move. For example, 10, I made it 20. Now I moved 20. Then I made 20 into 40, 40 into 80, 80 into 160. Then I moved 160. So my plan of moving 18 times 10 is binary represented as, what is the binary representation of 18? 18's binary representation is 10010, right? So what I do is, first I moved from C, this is moved from B, then this is moved from C, this is moved from C, this is moved from B. So from B I will move appropriate time. Now this is generic, this is true for any ABC, and then you can see that I am targeting a particular smaller bin and reduce the content. Because what you will have ultimately is, after removing maximum multiple times, the remainder will always be smaller. So I have an improved configuration. This configuration is closer to my goal. I apply now with respect to 6. I will get remainder of 6. It will be smaller. And when things become smaller and smaller and smaller, positive integers have got a great property. What is that property? You start from a positive integer, you make it smaller and smaller integer. It will hit 0. This may not be case for real numbers. Infinite time. You take 1, 1 by 2, 1 by 3, 1 by 4. It can be made smaller and smaller and smaller, but it will take infinitely many steps to hit 0. Right? Integers have a beautiful property that is called the well-ordering principle, fundamental property of integers, which you might have done, some of you, in your discrete math course. Beautiful property. Well-ordering principle tells that you are progressing, you will hit the goal, and you will hit the goal in finite number of steps. That is what it says. So now I have a beautiful computational procedure. Whatever is A, B and C, I will target the smallest jar. And how do I arrive at a smaller jar? I will use the second smallest one and try to move as many multiples of A from B as possible. How do I move as many multiples? Use the binary representation and wait for the appropriate doubling movement to move and then get the job done. Now you have a computational procedure available which is working for any ABC integers. If A or B or C are same, if any two of them are same, one step. If B equal to C, move from B to C, you have made it empty. Done. If all of them are distinct, here is the method which works on a beautiful algorithmic strategy or a computer called method of successive improvement, method of iterated improvement. Method of iterated improvement is a fundamental tool. It is used in graph algorithms, computational geometry, numerical methods, stringology, you name it, method of successive approximation. It is done in all kinds of searches in AI, ML, everywhere. You search for something, an optimal solution. You start with a near optimal solution. Do some locally optimal improvement and go for a better solution. Iterate it until you hit the optimum solution. This strategy, method of iterated improvement, is a paradigm, a powerful idea. It's a fantastic computational paradigm. Fine. How many times you will be moving from one jar to another in this process? That is algorithmic thinking. I have now a computational procedure, but then how many times I will do and then finally arrive at, am I doing a lot of water transfers? Is there a smarter way that with less number of transfers, that is with less number of operations, can I solve this problem? That is algorithmic thinking. Welcome to the exciting world of algorithmic thinking. Thank you very much. Any question? I have stopped with computational thinking, but algorithmic thinking, I leave it to you. You try and then have fun with this problem. Okay.